Hello everyone, and welcome back to Algebra 1 with Miss Betsy. Today what we're going to be doing is discussing how we deal with complex rational expressions. Now, they're not called complex because it's difficult to deal with solving these rational expressions. They're called complex rational expressions because of the form that they take. Before we start that, though, I want to ask you a brain teaser today instead of a lame joke. Now, there's this guy, and he built himself a rectangular house. Has windows on all four sides of this rectangle, and no matter which window he looks out, he always looks to the south. One day he's looking out, and a bear walks through his yard. And I want you to tell me what color that bear is, and I want you to tell me how you know what color that bear is. So I'll give you a second to think about that. And I'll tell you that it's a polar bear. So it's a white bear. First off, it's white. It's a polar bear because the only place that you could be where you have a house and every side of the house that you look out, you're looking to the south, would be if that house were sitting on the North Pole. Because you can't go north, can't go south from the North Pole. So it's a polar bear, which is white. If you are tracking along with me, I am on page 506 of my text. It's section 12.7, and it's entitled Complex Rational Expressions. My book is Algebra 1 for Christian Schools. It's published by Bob Jones University Press, and I'm using the second edition. But as with all of my algebra videos, it doesn't matter what book you're using. You're going to be using the same methodologies to solve these types of problems, so this should be helpful to you. Now, before we can learn how to deal with complex rational expressions, so we have to learn exactly what is a complex rational expression. And I'm going to introduce this by showing you our math problem here. You learned how to divide fractions by realizing and being taught that when you divide by a fraction, it's the same as multiplying by the reciprocal of the divisor. In other words, you turn that second fraction upside down, and it becomes a multiplication problem. Cancel common factors, and you end up with 2/3 as a solution to this division problem. 1/2 of 3/4. 1/2 divided by 3/4 is 2/3. Okay? This was just a simple math problem, simple fraction problem. We could also write it, though, by saying 1/2 divided by 3/4. And up to this point, we've really not used that because that's just a pretty complicated looking thing, and you don't really know how to deal with a problem that looks like that. But you do know that when you divide by a fraction, divide by a fraction, divide by a fraction, that you multiply by the reciprocal. And this is a procedure that this is a similar process that we're going to use when we work with complex rational expressions. So what we have right over here to this side of the board here is called a complex fraction. A complex rational expression contains variables someplace. So a complex rational expression can have variables either in the numerator, the denominator, or both. Now let me go ahead and give you a couple examples. If we have x over y divided by 4x, that's an example of a complex rational expression because it has a rational expression in the numerator, something written in the form a over b. Rational expression in the numerator. Here's another one. We have x plus 2 over x squared divided by x plus 2 over x. And you look at right now and you're probably going, ah! This problem here is actually very easy to solve, and we'll use it as one of our examples. But this is also a complex rational expression. It contains a rational expression in the numerator and a rational expression in the denominator. Here's another example of a rational expression. We have x squared plus 3x minus 9 over x plus 2 divided by x cubed. It still looks really strange, but it's a rational expression. This time, the denominator has the rational expression. This time, the numerator has a rational expression. Both the numerator and the denominator in our second example contain rational expressions. So these are called complex rational expressions. And the purpose of this lecture, what we're learning in this section, is how you simplify complex rational expressions. And we're going to see that we have two methods that we can use to solve these complex rational expressions. One of them is the one that I prefer, and they call this method 2. It's where we use the principle that division is the same as multiplying by the reciprocal. And then we have the first method, which is where we're going to multiply the numerator and the denominator by the least common multiple of the expression in the numerator and the expression in the denominator. Now, I'm not going to take the time to write the methodology down, but if you are in my actual physical class, I want you to make sure that you look at the bottom of page 507. There is a list here of what you do to simplify complex rational expressions, and it steps out for you in words what you need to do to solve these expressions depending on which method you use. Makes no difference at all which method you choose to use. I want you to use the one that makes sense to you. Some of you will say, oh, I like the first method best. Some of you will say, oh, Miss Betsy, I like your way best, where you're multiplying by the reciprocal of the divisor. Some of you say, it doesn't make any difference to me. I'll just use whichever one feels best, whichever one seems to fit the situation. Just know that there are two ways that you could solve these problems, and I'm going to do every one of my examples both ways, and I'm going to show you one particular type of complex rational expression where it really does seem to work most easy, most expeditiously to use the first method. Okay? Example 1 says, let's simplify x over y divided by 4. And I'm hoping that you can hear me talk, because I'm going out to the other room to get a marker that I carried out while I was checking on something. This is where it would be very convenient to have a pause on a remote pause, but I don't, so I'm clearly back now. We want to simplify x over y divided by 4. This is a complex rational expression because the numerator is a rational expression. Now, the first method that we're going to use, I'm going to say that this is method 1, and this is where we use the least common multiple of the denominators that are occurring in both the numerator and the denominator. Now, the way that your book uses the words to describe this, it's find the least common multiple of the rational expressions in the numerator and the denominator. What is the least common multiple of this expression and this expression? Well, the least common multiple here is going to be simply y, because 4 is just 4 over 1. So we're going to multiply the numerator and the denominator by that least common multiple. Y over y is just a value of 1. Now, if I write in for you y over 1, this should jump out to you now that we have a common factor of y in that rational expression in the numerator that we can cancel. What does that leave us in the numerator? We have x. What do we have in our denominator now? We simply have 4 times y. So the solution to this problem, to our original problem that we had that might have looked just really more than a little bit strange to you, x over y divided by 4, isn't hard at all to do. Now let me show you the second method. This is method 2. And this is invert and multiply. I'm going to be writing down every step that I'm doing here so that you see that this is very, very straightforward. We have x over y, all of this divided by 4. I'm using this separate, different color here to show my fraction bar. X over y divided by 4. Well, I'm going to go ahead and write that using that traditional division symbol when you're dealing with fractions. So you have x over y divided by 4. We know that when you're multiplying rational expressions, when you are dividing rational expressions, you invert and multiply. So this becomes x over y times 1 over 4. Multiply the numerators, multiply the denominators together, and you see, as you would certainly expect and as would be necessary if what we're doing is true, that it doesn't matter which method you use to simplify complex rational expressions, you end up with the same result. Whether you multiply numerator and denominator by the LCM of the rational expressions, or whether you convert this into a more traditional looking division problem that you solve by multiplying by the reciprocal of that divisor. Okay, so let's go ahead and look at example number 2. And this was our example of a complex rational expression where both the numerator and the denominator themselves are rational expressions. So we have, and I'm on page 507, example 2, x plus 2 over x squared, x plus 2 over x. X plus 2 over x squared divided by x plus 2 over x. What's the least common multiple of these two rational expressions? One denominator is x squared, the other denominator is x. We take each factor the greatest number of times it appears to come up with our least common multiple. So our least common multiple, which should just jump out at you real clearly, is x squared. So what are we going to do now? As I find my marker cap, what we're going to do is multiply the numerator and the denominator by that least common multiple. X squared divided by x squared has a value of 1. If it would help you to clearly see what we're doing, Now you see that we have two rational expressions that we're multiplying together in the numerator. We have two rational expressions that you're multiplying together in the denominator. You have common factors that you cancel. Common factor of x squared in the numerator and a common factor of x in the denominator. Multiply the numerators and denominators together. What do you have? You have x plus 2 over x times, look at that. We have another set of common factors. We have this binomial common factor of x plus 2 that cancels, coming up with our solution to this problem being 1 over x. Now, let's use this different method here where we are actually multiplying, inverting and multiplying. We started off with x plus 2 over x squared, all of that divided by x plus 2 over x. Let me go ahead and rewrite this as a traditional division problem. X plus 2 over x squared divided by x plus 2 over x. Now we know that the way that we divide is by multiplying by the reciprocal. Let's show the whole way. Yes, by multiplying by the reciprocal. We have x plus 2 over x squared times, now we're going to invert this, and we have x over x plus 2. Remember, you can only cancel entire factors. So we have a factor of x plus 2 that we cancel. We also have a factor of x that cancels, leaving us with the rational expression 1 over x as the solution to this problem. So you see, it looks weird and it can look intimidating, but if you just simply apply the principles that you know how to do, multiplying by common denominator, inverting and multiplying, you can solve these problems, but you've got to be careful not to get all caught up or lost in this work that's going on. Okay? Now we're at the bottom of page 507 where it is explaining to you what you're going to do to simplify complex rational expressions, whether you're using method 1 or method 2. Here we simply multiply numerator and denominator by the least common multiple of the rational expressions. Do whatever cancellation is necessary. What are you going to do here? Sometimes you might have to simplify the numerator and denominator separately. You're going to rewrite this as a division problem. And then you're going to, just like I said, multiply by the reciprocal of that divisor. Cancel common factors. Okay, even though I'm not writing these steps out, I'm explaining them to you as I go, and I'm illustrating them for you, but if it would help you to write out these algorithms, if you are, these plans, go ahead and do that. It makes it easier for some people. Now we're on the next page. We're going to do example 3. And this example is the one where it really is easier to multiply by the least common multiple. So we're going to go ahead and do this using method 1 first. I just changed my mind the order in which I wanted to do these. In our numerator we have 1 plus a squared over b squared. In our denominator we have 1 minus a over b. 1 minus a over b. Now at this point I would expect you to say, oh, that is really strange looking. This is still a rational expression. It's the sum of rational expressions. We've got the difference of rational expressions. If you have the sum of two fractions, what do you have to do? Find a common denominator and add. Have the sum, the difference, you find a common denominator and subtract. That's what we're going to have to do when we use the second method. But all we're going to do now here, this is the one where I said our first method, we can multiply by the common denominator of the rational expressions. What's our common denominator? We have a denominator of b squared. We have a denominator of b. What's our common denominator, our least common multiple? It's going to be b squared. So we are going to multiply both the numerator and the denominator by b squared. And what are we going to have to do here? We have to distribute, don't we? Now let me glance at this. I want to check something really quickly. Okay? Let's work on the numerator first. What do we have? We have b squared times 1, or 1 times b squared. And we have b squared plus a squared b squared times a squared. B squareds cancel here, don't they? So we have b squared plus a squared. B squared times 1 is b squared. When we multiply these two together, b squared times a squared over b squared, our factor of b squared cancels out. Let me just go ahead and write this because I'm not convinced that you necessarily are seeing what we're doing. Let me write that extra step in. What do we have in our denominator now? B squared times 1 is b squared minus ab squared over b. Now, we have common factors here that cancel, don't we? And we can do that because I couldn't cancel b squared this way, because that's canceling within terms. I can cancel the b squared in this because this is numerator and denominator of the same expression. So what? Same thing here. I can't cancel b from here, but I can cancel out a factor of b because I'm simplifying this one rational expression that is a part of the denominator. Let me move over here and see what I have left. B squared plus a squared over b squared minus ab. Everybody see what I've done here? B squared plus a squared. Here we've canceled a b, but we still have one factor of b remaining, so it becomes b squared minus ab. Now we have to make certain that we have no common factors. So we have b squared plus a squared over b times b minus a. Everybody look at that and make sure that makes sense to you. Now you might be saying, you didn't factor this. This should be b plus a times b minus a. No, what we have right here, this is the sum of two squares. So the difference of two squares would factor into b minus a, b plus a. So there's nothing that you can cancel. You go ahead and write this down here for our solution. B squared plus a squared over b times b minus a. Now we're going to go ahead and do our second method of solving this problem. I've erased part of the work, but that's all right. I'm concerned about the solution. In our numerator, we have 1 plus a squared over b squared. In our denominator, we have 1 minus a over b. Now, before we're able to invert and multiply, we have to rewrite the numerator and the fraction and the denominator as common fraction, with a common denominator. What denominator do we have here? We have b squared. So how are we going to rewrite this? Well, this is going to be b squared over b squared plus a squared over b squared, isn't it? Which is going to give us b squared plus a squared over b squared. In our denominator, we're going to have b over b minus a over b. So we have to be able to combine these two rational expressions. Now, in this numerator here, same denominator, so we have b squared plus a squared over b squared. That's how we combine these two rational expressions. B squared plus a squared over b squared. All of this is over b minus a over b. Now we're at the place where we can rewrite this division problem. And I am so totally and completely out of board space, it's not even crazy. It is crazy, it's not even funny. We have b squared plus a squared over b squared divided by b minus a over b. Everybody all right? What I've done here, we've written each expression with a common denominator, each term with a common denominator, so that we have a rational expression in the numerator, rational expression in the denominator, convert to the division of two rational expressions, so that instead of dividing, we're going to multiply by the reciprocal. Okay? Let me go ahead now and erase part of this work. This is why I've said that when you are doing these videos, if you're in my class, you really need to be working right along with me on your own sheet of paper. B squared plus a squared divided by b squared over b squared divided by b minus a over b. Going to change this now by saying we are going to multiply by the reciprocal of the divisor times b over b minus a. What do we see here for common factors? Remember, this is not the difference of two squares. This does not factor into b minus a times b plus a. The only factors that we have in common are a factor of b. So that leaves for us as our solution b squared plus a squared over b times b minus a. B squared plus a squared, b times b minus a. Same thing, two different methodologies. This type of a problem is challenging. If your brain is on overload now, I understand, but you can do these. Don't care which method you use, pick whichever one works well for you. So let's go ahead and do one final example here. As soon as I get this board erased. And I don't know if I have any coffee left. I do. I need to have a drink. We have x squared minus 9 over 4x. X squared minus 9 over 4x. All of this is going to be divided by x plus 3 over 8x squared. And we're going to use first method here, which says that we multiply the numerator and denominator by the least common multiple of these rational expressions. We have 4x, we have 8x squared. Our least common multiple is 8x squared. So we're going to multiply the numerator by 8x squared. We're going to multiply the denominator by 8x squared. And then we're going to go ahead now and cancel common factors. Remember, it's just the same as multiplying by 8x squared over 1. We have a common factor in the denominator that cancels of 8x squared. And our numerator, when we cancel 4x, what we have remaining in the denominator is 2x. Okay, let me verify that I'm doing this correctly. What do we have left now? We have 2x times x squared minus 9, all of this over x plus 3. Does anybody see what's happening here? Yeah, we do now have the difference of two squares. 2x times x plus 3 times x minus 3. All of this over a factor of x plus 3. We now have two binomial factors in common. X plus 3. We have one binomial factor that's in common. We have the same binomial factor in the numerator and in the denominator. What do we have remaining? 2x times x minus 3. We have nothing in the denominator now. To finish this, we want to distribute. So our solution is 2x squared minus 6. This is one way that you can solve this problem. This is actually method 1, where we're multiplying numerator and denominator by the least common multiple of both rational expressions. Now, for the final part of our lecture today, we're going to redo this problem, multiplying by the reciprocal. So if your problem looked like this, x squared minus 9 over 4x, all of that divided by x plus 3 over 8x cubed, you can rewrite that as a more traditional looking division problem, because once you have it in this form, you're going to, I'm missing something here, 2x, x cubed. Okay, see what I did? I changed my problem. I have 8x cubed, 8x squared. It's an advantage of being the teacher and looking ahead and saying, oops, I'm ending up with a problem here. 8x squared. We're going to multiply by the reciprocal. And as I write my step this time, I see that I've got x squared minus 9. I'm going to go ahead and factor this. Factor this difference of two squares. X plus 3 times x minus 3 divided by 4x multiplied by the reciprocal, 8x squared over x plus 3. It's very straightforward now to cancel common factors. You have x plus 3 that cancels. You have a factor of 4x that cancels. What you have remaining here is your 2x. You now have 2x times the quantity x minus 3. Didn't need to write that division bar, did I? We have a denominator of 1. You distribute your 2x. 2x times x is 2x squared. 2x times a negative 3 is a minus 6. And once again, it doesn't matter which method you use, you end up with the same result. And that's the end of this lecture on complex fractions. My kids, take your time, send me a text if you get frustrated. Hang in there, we're almost done. See you next time.